The setup described involves sharing a neutral conductor among multiple circuits. This is generally not allowed unless all of the following conditions are met. Firstly, the circuits are of the same voltage and frequency. Secondly, the circuits are protected by overcurrent devices of equal or lesser rating. And thirdly, the neutral conductor is sized to carry the maximum unbalanced current from all of the circuits. In this specific case, the neutral conductor is shared among 3 circuits protected by a 15 amps breaker. The neutral conductor should be sized to carry at least 15 amps. But the 14 American wire gauge THHN conductor is only rated for 15 amps at 60 degrees Celsius. The 2½ inch Greenfield conduits are likely not large enough to accommodate all of the conductors. According to the National Electrical Code, a 2½ inch conduit can accommodate 3 number 14 THHN conductors plus 1 number 10 THHN conductor plus 1 number 12 THHN conductor, or 2 number 14 THHN conductors plus 2 number 12 THHN conductors. The described setup includes 6 number 14 THHN conductors and 1 number 12 American wire gauge ground conductor, which likely exceeds the capacity of the conduit. Based on the concerns raised, the setup described may not be compliant with the National Electrical Code. The neutral conductor may not be adequately sized, and the conduit may not be large enough to accommodate all of the conductors. To bring the setup into compliance, the following steps can be taken. Firstly, install a separate neutral conductor for each circuit. This will eliminate the neutral sharing issue. Secondly, use larger conduits such as 3/4 inch conduits or Greenfields that will be required to accommodate all of the conductors. If a decision is made to use 12 American wire gauge conductors instead of 14 American wire gauge, the conduit size may need to be increased to 1 inch. Additionally, the overcurrent devices protecting the circuits will need to be adjusted to match the ampacity of the 12 American wire gauge conductors. The National Electrical Code addresses the requirements for neutral conductors in sections 300.3, B 310.15 and 215.4. Section 300.3, B covers the general requirements for conductors of the same circuit. All conductors of the circuit, including the neutral, must be run together in the same raceway or cable. This ensures that the magnetic fields produced by the conductors cancel each other out, reducing inductive reactance and voltage drop. Section 310.15 details the allowable ampacities of insulated conductors. The ampacity of a conductor is the maximum current, in amps, that it can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and the ambient temperature. For example, a 14 American wire gauge THHN conductor has an ampacity of 15 amps at 60 degrees Celsius, 20 amps at 75 degrees Celsius, and 25 amps at 90 degrees Celsius. However, the lower temperature rating of 60 degrees Celsius is often used for practical applications. A 12 American wire gauge THHN conductor has an ampacity of 20 amps at 60 degrees Celsius, 25 amps at 75 degrees Celsius, and 30 amps at 90 degrees Celsius. Section 215.4 specifically addresses neutral conductors. It states that a neutral conductor must have sufficient ampacity to carry the maximum unbalanced current. The unbalanced current is the maximum difference between the currents on the ungrounded conductors. For example, if there are 3 circuits each drawing 15 amps and the loads are balanced, the neutral current will be 0. However, if one circuit is drawing 15 amps and the other 2 are not drawing any current, the neutral current will be 15 amps. In this case, the neutral conductor must be sized to carry at least 15 amps. The National Electrical Code also covers the requirements for conduit fill in Chapter 9, Note 1 to Table 1. Conduit fill refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The National Electrical Code specifies maximum allowable conduit fill percentages to ensure that there is adequate space for heat dissipation and to prevent damage to the conductors during installation. The allowable fill percentage depends on the number of conductors in the conduit and the type of conduit. For example, for 3 or more conductors in a conduit, the maximum allowable fill percentage is 40%. To calculate the conduit fill, you need to know the cross-sectional area of the conductors and the cross-sectional area of the conduit. The cross-sectional area of a conductor can be found in Chapter 9, Table 5 of the National Electrical Code. The cross-sectional area of a conduit can be found in Chapter 9, Table 4 of the National Electrical Code. For example, the cross-sectional area of a 14 American wire gauge THHN conductor is 0.81 square inches, and the cross-sectional area of a 12 American wire gauge THHN conductor is 0.133 square inches. The cross-sectional area of a 1/2-inch electrical metallic tubing EMT conduit is 0.304 square inches, and the cross-sectional area of a 3/4-inch electrical metallic tubing EMT conduit is 0.533 square inches. To determine if the conductors fit within the conduit, the total cross-sectional area of the conductors is calculated and compared to the allowable fill area of the conduit. The allowable fill area is calculated by multiplying the cross-sectional area of the conduit by the allowable fill percentage. For example, if there are 6 number 14 American wire gauge THHN conductors and 1 number 12 American wire gauge ground conductor in a 1/2-inch electrical metallic tubing EMT conduit, the total cross-sectional area of the conductors is 6*0.81 plus 0.133 equals 0.619 square inches. The allowable fill area of the 1/2-inch electrical metallic tubing EMT conduit is 0.304 *0.40 equals 0.1216 square inches. Since 0.619 square inches is less than 0.1216 square inches, the conductors fit within the conduit. However, if the conduit is 3/8-inch flexible metal conduit, which has an allowable fill area of only 0.8 square inches, the conductors would not fit. Sharing a neutral conductor among multiple circuits, also known as a multi-wire branch circuit, is permitted under certain conditions, but it requires careful consideration to ensure safety and compliance with the National Electrical Code. A multi-wire branch circuit is a circuit that consists of 2 or more ungrounded conductors that have a voltage between them, and a neutral conductor that is common to all of the ungrounded conductors. These circuits are commonly used in residential and commercial buildings to provide multiple 120 volt circuits from a 240 volts or 208 volt supply. The main advantage of using a multi-wire branch circuit is that it saves on materials and labor costs, as only one neutral conductor is required for multiple circuits. However, there are also some potential safety hazards associated with multi-wire branch circuits, such as the risk of overloading the neutral conductor or creating an open neutral condition. To ensure safety and compliance with the National Electrical Code, the following requirements must be met when using a multi-wire branch circuit. Firstly, all of the circuits must originate from the same panel board. This is to ensure that all of the circuits are supplied from the same source and that the neutral conductor is properly grounded. Secondly, the neutral conductor must be sized to carry the maximum unbalanced load. This is to prevent the neutral conductor from overheating and potentially causing a fire. The maximum unbalanced load is the maximum difference between the currents on the ungrounded conductors. For example, if there are 2 120 volt circuits sharing a neutral conductor, and one circuit is drawing 15 amps while the other is drawing 10 amps, the unbalanced load is 5 amps. In this case, the neutral conductor must be sized to carry at least 5 amps. Typically, the neutral conductor is the same size as the ungrounded conductors, but in some cases, it may need to be larger. Thirdly, a common disconnect must be used for all of the circuits. This is to ensure that all of the circuits can be disconnected simultaneously, which is important for safety and maintenance purposes. The common disconnect can be a circuit breaker or a switch. Fourthly, the circuits must be arranged so that the neutral conductor is not overloaded. This can be achieved by balancing the loads and the different circuits. For example, if there are 2 120 volt circuits sharing a neutral conductor, the loads on the 2 circuits should be approximately equal. This will minimize the current on the neutral conductor and reduce the risk of overloading it. Fifthly, if using individual conductors in a raceway, all conductors of the multi-wire branch circuit, including the neutral, must be run together in the same raceway. This is to ensure that the magnetic fields produced by the conductors cancel each other out, reducing inductive reactance and voltage drop. If the neutral conductor is not run with the ungrounded conductors, it can create a significant voltage drop, which can cause equipment to malfunction. The National Electrical Code also requires that multi-wire branch circuits be identified in the panel board. This can be done by labeling the circuit breakers or by using a common tie bar to connect the circuit breakers together. The purpose of this requirement is to make it easier for electricians to identify multi-wire branch circuits and to avoid accidentally disconnecting the neutral conductor. If the neutral conductor is disconnected while the circuits are energized, it can create a dangerous overvoltage condition. An open neutral condition can occur when the neutral conductor of a multi-wire branch circuit is disconnected or broken. This can happen for a number of reasons, such as a loose connection, a damaged conductor, or a faulty circuit breaker. When an open neutral condition occurs, the voltage on the different circuits can become unbalanced, which can cause equipment to malfunction or even be damaged. For example, if there are two 120-volt circuits sharing a neutral conductor, and the neutral conductor is open, one circuit may have a voltage of 180 volts while the other circuit has a voltage of 60 volts. This can damage sensitive electronic equipment such as computers and televisions. In addition to the risk of equipment damage, an open neutral condition can also create a shock hazard. If a person touches a grounded metal object while the neutral conductor is open, they can receive a shock. To prevent open neutral conditions, it is important to ensure that all connections are tight and that the conductors are properly protected from damage. It is also important to use high-quality circuit breakers and to periodically inspect the electrical system for any signs of wear or damage. Grounding is a critical aspect of electrical safety and is essential for protecting people and equipment from electrical shock and fire hazards. The National Electrical Code provides detailed requirements for grounding electrical systems, and it is important to follow these requirements carefully. Grounding is the process of connecting the non-current carrying metal parts of an electrical system to the earth. This includes the metal enclosures of equipment, the metal raceways that enclose conductors, and the metal frames of buildings. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source. This allows the overcurrent protection devices such as circuit breakers or fuses to quickly trip and to energize the circuit, preventing electrical shock and fire hazards. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding is the process of connecting the non-current carrying metal parts of an electrical system to the earth. This is typically done by connecting a grounding conductor from the equipment to a grounding electrode, such as a ground rod or a metal water pipe. System grounding is the process of connecting the neutral conductor of an electrical system to the earth. This is typically done at the service entrance, where the electrical service enters the building. The purpose of system grounding is to stabilize the voltage of the electrical system and to provide a low impedance path for fault current to flow back to the source. The National Electrical Code requires that all electrical systems be grounded. The specific requirements for grounding depend on the type of electrical system and the voltage. For example, for a 120/240 volt single-phase system, the National Electrical Code requires that the neutral conductor be grounded at the service entrance. The grounding electrode must be a metal water pipe that is in direct contact with the earth for at least 10 feet, or a ground rod that is at least 8 feet long and is driven into the earth. The grounding conductor must be sized according to the size of the service entrance conductors. For example, for a 200 amp service, the grounding conductor must be at least number 6 American wire gauge copper. In addition to the requirements for grounding at the service entrance, the National Electrical Code also requires that all equipment be grounded. This includes appliances, lighting fixtures, and other electrical equipment. The equipment grounding conductor must be sized according to the size of the circuit conductors. For example, for a 20 amp circuit, the equipment grounding conductor must be at least number 12 American wire gauge copper. The equipment grounding conductor must be connected to the metal enclosure of the equipment and to the grounding electrode system. There are several different methods that can be used to connect the equipment grounding conductor to the grounding electrode system. One method is to use a grounding wire that is connected to the metal enclosure of the equipment and to the grounding electrode system. Another method is to use a metal raceway, such as electrical metallic tubing EMT conduit, to provide a path for the equipment grounding conductor. The metal raceway must be properly bonded to the metal enclosure of the equipment and to the grounding electrode system. Bonding is the process of connecting together all of the metal parts of an electrical system to create a low impedance path for fault current to flow. Bonding is important for preventing electrical shock hazards and for ensuring that the overcurrent protection devices will quickly trip and de-energize the circuit in the event of a fault. The National Electrical Code provides detailed requirements for bonding electrical systems. The specific requirements for bonding depend on the type of electrical system and the voltage. For example, for a 120/240 volt single-phase system, the National Electrical Code requires that all metal water pipes, metal gas pipes, and metal raceways be bonded together. The bonding conductor must be sized according to the size of the service entrance conductors. For example, for a 200 amp service, the bonding conductor must be at least number 6 American wire gauge copper. In addition to the requirements for bonding at the service entrance, the National Electrical Code also requires that all equipment be bonded. This includes appliances, lighting fixtures, and other electrical equipment. The equipment bonding conductor must be sized according to the size of the circuit conductors. For example, for a 20 amp circuit, the equipment bonding conductor must be at least number 12 American wire gauge copper. The equipment bonding conductor must be connected to the metal enclosure of the equipment and to the grounding electrode system. Surge protection is another important aspect of electrical safety. Surges are sudden increases in voltage that can damage or destroy electronic equipment. Surges can be caused by lightning, power outages, or other electrical disturbances. The National Electrical Code recommends the use of surge protective devices (SPD) to protect electrical equipment from surges. SPD are devices that are designed to divert surge current away from sensitive electronic equipment. SPD are typically installed at the service entrance where the electrical service enters the building. SPD can also be installed at branch circuits to protect specific pieces of equipment. The National Electrical Code provides requirements for the installation of SPD. The specific requirements depend on the type of SPD and the location where it is installed. For example, the National Electrical Code requires that SPD installed at the service entrance be connected to the grounding electrode system. The National Electrical Code also requires that SPD be listed and labeled for the intended use. Arc fault circuit interrupters of size are another important safety device that can help to prevent electrical fires. A size are circuit breakers that are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when there is a break in the insulation of a wire or when there is a loose connection. When an arc fault occurs, the electrical current can jump across the gap, creating a high-temperature arc that can ignite nearby combustible materials. The National Electrical Code requires the use of a size in many areas of the home, including bedrooms, living rooms, and dining rooms. A size are designed to trip and de-energize the circuit when an arc fault is detected, preventing a fire. Ground fault circuit interrupters (GFCIs) are another important safety device that can help to prevent electrical shock. GFCIs are circuit breakers that are designed to detect ground faults, which are dangerous electrical conditions that can cause electrical shock. Ground faults can occur when electrical current flows through an unintended path to ground, such as through a person's body. The National Electrical Code requires the use of GFCIs in many areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to trip and energize the circuit when a ground fault is detected, preventing electrical shock. The National Electrical Code is a comprehensive set of standards that provides requirements for the safe installation of electrical systems. It is important for all electricians and electrical contractors to be familiar with the National Electrical Code and to follow its requirements carefully. The National Electrical Code is updated every 3 years, so it is important to stay up to date on the latest changes. The National Electrical Code is published by the National Fire Protection Association (NFPA). The National Fire Protection Association (NFPA) also offers a variety of training courses and resources to help electricians and electrical contractors stay up to date on the latest electrical safety standards. In addition to the National Electrical Code, there are also many other electrical safety standards and regulations that may apply to a particular installation. It is important to check with the local building department to determine which standards and regulations apply. Electrical safety is a critical concern, and it is important to take all necessary precautions to prevent electrical shock and fire hazards. By following the requirements of the National Electrical Code and other applicable standards and regulations, it is possible to create a safe and reliable electrical system. Always consult with a qualified electrician or electrical contractor before performing any electrical work.